Um, hi everyone. My name is Fernando Rodriguez, and I'm gonna be presenting Strange Mental Machines, work that we did with Adam and Phil, all of us from the University of Sussex. Okay, so since the beginning, more or less, of the last century, there's been this question about the nature of the relation between cognition and computation, right? And the main idea here is that systems that we understand as intelligent systems, they can be described to some extent as computers, right? I mean, the original idea when cognitive science gets, let's say, together when it's born, was that, given information that we had from psychology and linguistics and other fields in the frame of AI just starting, it basically, the conclusion, the original conclusion was that brains and human intelligence basically were a form of computation. So basically, our brains were physical instances of computer systems, what was famously known as the physical symbol systems hypothesis, right? The idea that intelligence need symbols, and because we live in a material universe, in order to produce intelligence, we had to physically instantiate these symbols. Then, mostly in parallel, we have this approach to cognition that comes from cybernetics, which is rather has to do with life, right, with living beings and the properties of living beings. And we could think of autopoiesis in this sense as a kind of concretion of or a culmination of the work made from cybernetics, in the sense that autopoiesis can be seen as a feedback loop maintaining a feedback loop itself, right? What we understand as the organization, and this idea of biology and cognition. So basically, the idea that it is from life that we understand what cognition is, or that we have autopoiesis, autonomy, then enactive autonomy. And in theory, this approach has an inherent phenomenological dimension, and an idea that life presupposes some kind of mind, let's say, to some extent, or the origin of mind. However, this approach, right, it has taken this set of properties, like the ones that this kind of cycle of operational closure, informational closure, has resulted in this idea of in the one we have the Ouroboros, which is an idea very emphasized by enactivism and autonomy and autopoiesis. This idea that the whole system produces itself, and the operations are a result of this kind of recursive operation of the system, which leads to a kind of very mechanistic approach at the end, right? And this is what we have now in contemporary enactive cognitive science. Basically, we have returned to a point which is very much the same as from when we started, right? So we have a lot of understanding now about the mechanistic processes that guide behavior, and intelligent behavior in particular, but we don't really understand anything, the more that we know about this, the less that we understand the step that we need to have from these mechanisms into minds. Well, what is the gap here, right? And so, as a summary of this first part, we have that on the one hand, this is an uneasy acknowledgement to do, right? That basically cognitivism and enactivism has led us to the same place. The idea that on the one hand we have these kind of properties that make intelligence possible, very much stable, consistent mechanisms and recursion, and on the other hand, there's this fundamental difference between these kind of properties that we can describe and what we understand, and from our very much our own point of view, when we see as a mental life, right? And that includes any kind of very specific phenomena that appears with a mental life as I mean, at least as we understand, as we live it, right? Phenomenology, temporality, agency, etc. Okay, so this is one of the first points, the key points that I want to make, and the idea is that if by cognition we label the kind of properties that appear with life, right? And a different discussion is if every living being is conscious, right? But I think life in itself is a very specific phenomenon. So if we think so, to label cognitive systems, I mean to label living systems as cognitive, very much is something that is very specific to them, right? On the other side, we have on the other extreme, let's say, of this kind of very simple map, we have natural mechanisms, which are, let's say, they are the basis for what we can understand as computation. Because even if we have this very nice paper from Pérez Mercader about how chemistry computes, the idea is that the problem is that for computation, in this sense, you need an observer, right? And there's no observer in these kind of mechanical steps if there's no recursion. In this case, the experimenter is the one making the experiment, so let's say demonstrating or proving that there's a consistency, a mechanistic consistency in the chemical processes, but there's no observer in the processes themselves, or the observer not in the conscious mean of the observer, right? But in the let's say our pink area here, that we have autonomous systems, here's when we have protocognitive properties, right? When we have the set of properties that precede life, right? But that that stem from recursive dynamics and stable, consistent mechanisms. So when you have in a computer, let's say this is a classical example of Turing machines about natural numbers. When you have natural numbers, it's not that you need for them to be natural numbers, right? The idea is that you need symbols that are fixed, so you could do 1 plus 1, and 1 plus 1 is always going to give you 2, and it's not sometimes going to give you 3 or 4, right? So basically you need consistent mechanisms but which you have in the blue area here. That's the idea, But the idea is that in operationally closed systems, like autonomous systems, then you have um, a self-production, so a maintenance of these kind of symbols, right? Because the system creates the elements, and the elements create the network of processes that create the system itself, right? So basically, what you're saying is, what you're doing is maintaining the, let's say, regenerating the state table of the Turing machine, if you want to see it like that. So we have here a physical implementation or a physical instantiation of the mathematical abstraction that we understand as computation. And and this leads us to a very kind of complex point, because the whole idea of protocognitive properties lead us to the idea that we can explain most of what we understand as intelligence in mechanistic terms, right? And if you think so, if we go to the original paper of Turing's in 1936 on computable numbers, there's this distinction between automatic machines and choice machines, right? And by choice machines, it was intended the idea that machines that could make choices. In that case, the idea was from an external operator, and automatic machines, and all computation is based on the idea of automatic machines. So the ones that don't need a mind, they don't need to think. You don't. The idea is to automatize the processes, and to without any need for someone making decisions, right? And that kind of, I think, very much explain the point why it would be a problem if, or why is kind of contradictory to think that we can explain every kind of cognitive phenomenon in insofar as computable, while at the same time thinking or believing that we're going to understand agency in the same terms. And yeah, the last point that I want to make is, I think that artificial life is going to be the best arbiter of this conundrum that we currently have. So on the one hand, we have this computational protocognitive set of properties, right? That we understand how they work to a very kind of good extent. And on the other hand, we have this idea of life and mental life, and I think, because as I see it, artificial life is concerned of protocognitive properties. I think this is it basically is best possible domain to analyze, discuss, and probably solve someday this problem of, okay, at which point we have life, and on what is the difference between this kind of set of many mechanisms and something more, something beyond. And these are the conclusions. I'll talk a bit in the answers if you need. Thank you very much. Bye bye.
Good afternoon, ladies and gentlemen. I'm Jeongho Park, and I'm very honored to here standing in front of you. In today's presentation, I will present a homing navigation algorithm that incorporates the optical feature, enabling navigation toward a reference point in an indoor environment. The order of today's presentation is as follows. First, I will cover the introduction, which explains the overview and objectives of the research. Next, I will present the method and the result of the homing algorithm. And next, I will introduce the follow-up research and conclude my presentation. My research was inspired by the visual characteristics of insects like ants and bees. Ants possess a visual characteristic that allows them to see their entire surroundings in 360 degrees. This feature enables them to perceive environmental changes with a much wider field of view. Additionally, bees are able to estimate their flight distance by perceiving changes in the size of surrounding objects during flight. Inspired by these visual features of insects, we conduct research on navigation algorithm. In addition, insects possess a homing ability, allowing them to return to their nests without relying on GPS or maps. For example, desert ants use their own internal odometer to track how far they have moved. When they reach their destination, they can calculate the direction and distance from the starting point and return directly to their nests by the shortest path. In ordinary ants, after leaving their nests, they rely on the changes in surrounding landmarks they have observed to navigate their way back home. In this study, we aim to implement such homing characteristic of ants. The purpose of this presentation can be divided into three main points. First, inspired by the visual characteristics of insects, I will explain an algorithm that recognizes changes in landmarks between home and current position. Second, as shown in the GIF on the right side, I will introduce an algorithm that estimates the homing direction from various positions. Finally, I will present the result of testing our homing algorithm in multiple environments. The method section of our algorithm can be divided into three main sections. First, similar to the ant vision, we have an image transformation section. In this section, I will explain how the environment can be interpreted from the panorama perspective. Second, I will introduce the algorithm for detect landmarks on the image and matching the landmarks between home and current position. Finally, I will present the algorithm for determining the home direction based on this information. First, let me explain the image transformation section. The first step is to convert the omnidirectional view into a panorama view. The panorama view is an unfolded form of the omni view, where the horizontal axis represent to 0 degree to 360 degree. We can extract two important pieces from the figure below. In this example, from the current position, in order to reach the home position located in the center, the agent needs to head in 45-degree direction. At both the current position and the home position, landmark 2 lies at 45 degree, and landmark 3 lies at the opposite direction, 225 degree. If we convert the omnidirectional views into panorama view, we obtain the right-hand figure where landmarks are matched between the two locations. By tracing how the triangular landmarks around landmark 2, we can see that they converge towards landmark 2. Conversely, at 225 degree, the landmarks around landmark 3 diverge outward. Secondly, we detect distinct features from the panorama views captured at both positions. For feature extraction, we use the surf feature. Surf is based on the Harris corner detector, which identifies corner points in an image where the intensity changes significantly along both the x and y axis. Within the surf window, we can obtain descriptor vectors using the values of dx and dy, which are then using for matching. We extracted these descriptor vectors from both the home image and the current image and performed feature matching based on the filter scores, where the score differences were computed using the Euclidean distance formula. In the next section, we estimate the homing direction based on the matched feature pairs. The example at the top left shows a matching case where the homing direction from the current position is 50 degrees. We use converge and outward-based angular behavior of the matching pairs to estimate the homing direction. We define delta theta as the difference between the angle of a feature in the panorama image of the current and home position. When the pair diverges to the left, delta theta is negative, and when the pair diverges to the lower right, then delta theta is positive. When there is no angular difference, delta theta goes to 0. By plotting the panorama angle on the x-axis and delta theta on the y-axis, we obtain a scatter plot of the matched pairs in the angle theta domain. We discovered that transition of delta theta sign provides a hint for determining the home direction. When delta theta transitions from positive to negative, then location corresponds to the homing direction. However, when delta theta transitions from negative to positive, the location corresponds to the opposite direction. To identify these transition regions, we use a metric that detects strong lines in a scatter plot. A strong line is defined as the line intersecting with the largest number of scatter points. As mentioned, the homing direction in this case is around 50 degrees, and the strongest line is also located near 50 degrees. Based on this algorithm, we tested the performance in 4 different environments. The dataset labeled original served as the baseline test environment. Our rear and screen datasets introduce confusion by placing plant and a screen at the center of the original room. Finally, the whole one dataset represents a very challenging environment, being overall quite dark with the presence of light reflections. The figure on the left shows the vector maps representing the homing performance across the four datasets, and the red dot in the center of each vector map indicates the home position. Use it as the reference point. In the original and arboreal datasets, the vectors generally point toward the home from nearly all positions. However, in the screen dataset, poor homing performance can be observed in the region marked by the red dashed circle, where the screen is located. In the whole one dataset, the dark environments and light reflections reduce the accuracy of feature matching and leading to weaker homing performance overall. On the right, the table reports the average angular error across current positions in each environment. In the original and arboreal datasets, our algorithm showing an improvement of 10 to 15 degrees compared to other algorithms. Similarly, in the screen dataset, our algorithm also delivered the best performance. In contrast, in the whole one dataset, due to the dark setting and poor feature matching, performance was weak across all algorithms, including ours. Now, I would like to explain the additional research we have conducted. In the paper, we presented only the algorithm that identifies the most dominant line. However, this method has a critical limitation. It is vulnerable to noise structures in the scatter plot. To address this issue, we devised an algorithm that can robustly handle such noise components by employing a Gaussian model. Specifically, we identified the optimal Gaussian model within a local region compute the covariance from the Gaussian parameters, and then finally apply population coding to estimate the final homing angle. Unlike online line metrics, the Gaussian-based approach captures the overall shape of the distribution in the region. This allows it to reduce the impact of noise and provide more stable results. We conducted experiments in a real-world environment to evaluate our algorithm. For this, we used a turbo platform and mounted a camera on top of the robot to capture images in an omni view, mimicking the visual characteristic of ants. So far, we have introduced a method for navigating toward the home location from arbitrary position using visual information. However, in real environments, it is crucial to ensure stable homing even from longer distances. To achieve this, we applied the concept of milestones. In nature, ants memorize landmarks when they leave their nests, and later, during homing, they pass these landmarks in sequence to return home. We adopt the same principle as concept of milestones for robotic homing. The method we propose is the sequential homing strategy. It guides the robot back to the home location by retracing the previously recorded milestones in reverse order. The first step to achieve sequential homing strategy is for the robot to create milestones during each random exploring phase. The robot uses each odometry information to decide when to create a milestone point after it has traveled a sufficient distance from the previous one. Sorry. At the moment, it records a new milestone by capturing an omni-view image of the surroundings. The top of the image on the left is the milestone from the previous step, and the bottom image is from the current position. The robot performed a total of 101 movements, and you can see each trajectory on the screen. And when the robot finishes its random exploring, then the homing phase started. During the homing phase, the robot retraces these recorded milestones in reverse order, guiding itself back to the home location. You can see the robot in the homing phase. And finally, it reaches its home position safely. Let me conclude my research. First, inspired by the visual characteristics of insects, we conducted a study to detect features in images. Second, we proposed an algorithm that represents the result of optical characteristics as matched pairs in the scattered domain and identifies strong lines within that domain. Lastly, by comparing the performance of our method with other algorithms, we were able to demonstrate the robustness and accuracy of our approach. This is the end of our presentation. We hope our findings open new directions for both biology-inspired AI and robotics. Thanks for listening.